Section 4.1, polynomial functions. Okay, polynomial function is one that is smooth and continuous. The degree must be non-negative integer, so essentially whole numbers. So for example, if I ask you, is something like the f of x equals negative 1/2 x to the 4th plus 2x. The degree of this term is 4. Remember the highest exponent, that's the degree. The degree of the first term is 4. The degree of the second term is 1. So the answer is yes. This is a polynomial with a 4th degree. The second you see anything with fractions, I shouldn't say a fraction, something like 1 over x, 1 over x squared, not a polynomial. Any kind of roots, not a polynomial. Any kind of log, not a polynomial. So if you recall, polynomials all have end behavior. Polynomials all have end behavior, and there are 4 types of end behavior. Up, up, down, down, up, down, down, up. 4 types of end behavior. This would model x squared. X to the 4th, x to the 6th, x to the whatever. This is a is greater than 1. Sorry, the absolute value of a is greater than 0. Let's try that again. The absolute value of a is greater than 0, and it is an even degree. Down, down is even degree. And this is not right, sorry. This is a is greater than 0, and this is a is less than 0. My apologies. A is positive, a is negative. A is the lead coefficient. This would be odd degree, x cubed, x to the 5th, x to the 7th, x to the 9th, whatever. A is less than 0. And this is odd degree. And it says degree, a is greater than 0. So if you have something like the f of x is equal to negative 6x squared times the quantity x minus 1 to the 5th times the quantity x plus 1 to the 7th. The overall degree of this polynomial would be x squared. If you multiplied this out, you would have x to the 5th. If you multiplied this out, you would have x to the 7th for a total of 2 plus 5 plus 7, which is 14. A is negative. If you were to multiply this whole thing out, you would have negative 6 times 1x to the 5th times 1x to the 7th. So a would be less than 0. So this would be even degree, a less than 0. This would model an upside down parabola for your end behavior. Okay, so if I give you the zeros of the function, remember zeros are the same thing as the x-intercepts, same thing as the solutions. You know what, let's go back to this one. What are the zeros of this polynomial? The zeros of this polynomial set each factor equal to 0. This would be x-intercept at the origin. And the degree would be 2. The overall degree of this polynomial is 14, but the individual degree of the origin, the x-intercept at the origin, is 2. This would have an x-intercept at 1, 0. And the overall degree of this particular x-intercept would be 5. And here you would have negative 1, 0. And the degree would be 7. Also known as multiplicity. When you're talking about the individual degree, it's also referred to as multiplicity. So hopefully you remember from last year, if you have odd degree, the graph crosses at the x-intercept. And if you have even degree, bounce, or it's referred to as touching. I like to say bounce. Bounce is more fun. Bounce reminds me of Tigger. Okay, let's work backwards. If I give you the zeros of a function, you write the equation. So let's say you have given zeros at x equals 2, x equals 1, x equals 4. And I want you to write a potential equation of this function. Work backwards. If x equals 2 is a 0, x minus 2 is the factor. If x equals 1 is the 0, x minus 1 is the factor. If x equals 4 is the 0, x minus 4 is the factor. Okay, so that's one potential answer. That's the easiest one. And you don't need to multiply it out. There's no need to multiply it out. Let's do something a little bit more specific. Let me tell you this time that you are given a 0 at negative 1. But I'm going to tell you that the multi, is 2. And then you have a 0 at 0. And you have a 0 at 3, also with a multiplicity of 2. But now I'm telling you that it goes through a specific point. And I'm going to tell you that it passes through -48. In the previous example, we said A was 1, and I didn't tell you that it went through a specific point. We just said this is the generic equation. It might go through different points, but really all I care about are the zeros. Now I'm telling you we have zeros, x-intercepts, and it also goes through the point 1, -48. And this matters because it might change our end behavior. In this example, the degree is 3, A is positive. In the previous example, A is positive. If you were to multiply this whole thing out, which I told you you didn't need to do, nor we're not going to either right now, but if you did, you would have 1x times 1x times 1x, and the lead coefficient would be 1x. The lead coefficient would be 1 on the term 1x cubed. So A is greater than 0. The degree is 3, so this is down up. Now I'm telling you it goes through a specific point. Okay, so let's check this out. I'm going to tell you the function has some lead coefficient, which I don't know, a. It goes through -1 with a multiplicity of 2. So as a factor, that's x plus 1 squared. Goes through 0, that's the same thing as x. And then 3, which would be x minus 3 with a multiplicity of 2. But now I know that when x is 1, y is -48. When x is 1, y is -48. So y, f of x, same thing. So this is going to be -48 equals a 1 plus 1 squared times 1 times 1 minus 3 squared. A, you can use whatever letter you want, but generally we use A on the lead coefficient. AX squared plus BX plus C, right? Everything's based on A. You can use Q if you want. I don't recommend it. So you get -48 equals, this is 4 times 1 is 4 times -2, 4, 16, I believe. I believe this whole thing is 16. I've done it right. I don't have my calculator with me, so I'm just relying on my brain. 1 plus 1 is 2, 4 times 1 is 4, 1 minus 3 is 2 squares. Yeah, so A is -3. And this changes the end behavior of this function because A is negative. So the equation for this function is -3 x plus 1 quantity squared, x minus 3 quantity squared. Let's talk about turning points. Turning point is, we actually talked about turning points a little bit when the graph changes from increasing to decreasing. We talked about that when you were, I don't know, the last section we were looking at. You had to give intervals for increasing and decreasing, and I said it had to be a parenthesis because you didn't know if the graph was increasing or decreasing. It was turning at that point, hence a turning point. Okay. This has an overall degree of 3. If I were to multiply this out, I would have 2 times x squared blah, 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 who cares, times x blah, 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 who cares. I want the lead term, and the lead term would be 2x cubed. The lead term would be 2x cubed. So this is down up. It mirrors x cubed. Degree is odd. You have a 0 at -1. X equals -1. Multiplicity is 2. 2 is even, so this is a bounce. You have a x-intercept, x is 3. The multiplicity is 1. That's odd, so it crosses. Odd multiplicity crosses, even multiplicity bounces. Multiplicity right here is 2. Okay, the y-intercept, which you should also find. Plug in 0 for x and you get -6. Okay, I'm just going to draw like some not very good graph. Because the whole point of this is I want to talk about turning points. So here's -1, 1 to +3, -6 looks great right there. Who cares? And behavior is down, up, down, up. Okay, and I'm going to stop right here. So at -1, I bounce. Okay. So I'm going to bounce off -1, and I'm going to come down to -6. And then I'm going to go up and cross at 3. But how do you know that it goes straight up, that it's a nice smooth connection from the y-intercept to this x-intercept? How do you know that there's not some fun little loop-de-loop going on in between without using your graphing calculator? So there could be turning points going on in here. We could say, okay, the graph is increasing till we get to -1, and then it's decreasing to x is 0, but then it increases and it decreases and it increases. Like, how do we know what's going on in here? So if you remember all of these little points, so if I look at my y-intercept, and I'm increasing to here, and then I decrease to here. Without my calculator, I don't know, but each one of those would be called a turning point. Well, there's a rule for turning points. There's a rule for turning points, and as you wait patiently, the number of turning points, sorry, I forgot a word, the maximum number of turning points where the graph goes from increasing to decreasing and vice versa. The maximum number of turning points is equal to the degree minus 1. Well, remember I said to you up here, how do we know it doesn't look like this? Which would be pretty fun and cool, but this is not a possibility for the graph that I just drew, because in this particular example, the overall degree is 3. The overall degree of this function is 3, which means the maximum number of turning points it can have is 2. Well, if you see what I drew in, it increases, that's a turning point. At the y-intercept, that's a turning point. Uh-oh, another turning point, another turning point. I drew in 1, 2, 3, 4. I drew in 4 turning points, and that's not possible. So the only possibility for what this graph can look like, so let's just redraw this, -6, -1, it bounces to -6, 1, 2, 3. Wow, it's not a very smooth curve. My other one looked better, but this is what the graph must look like. Up, increasing, boom, turning point. X is 0, turning point, back up. This has 1, 2 turning points, and this is the only possibility for what this graph can look like. And that is, that's it.